Next, we will study about schedulers. Okay, so the process will migrate among various scheduling queues throughout its lifetime. Right? In the previous slide, we had studied this one. Right? So the operating system it must select for scheduling purposes processes from this queue in some fashion. Now the selection process is carried out by a appropriate scheduler. So you have two types of schedulers. One is long-term scheduler or job scheduler. Another one is short-term scheduler or CPU scheduler. Okay. So if you have a batch processing system, so what will happen here is more processes would be submitted and that can be executed immediately. So these processes are spooled to a mass storage devices, or they'll be kept in a mass storage devices. So whenever they are kept in the disk, they would be executed, or for later execution they are kept there. So the long term schedulers it will come into picture, or as the name suggests it is job scheduler. Okay, so this selects a process, or it selects multiple processes from that job pool or the job queue and loads them into the memory for execution. Okay, I'll okay, so let's get back to this picture where it is called as job pool or job queue. Okay, so this job pool or the job queue it will have multiple programs or processes, right? So up to like pn. Okay, so whenever these processes or you store the program, it would be typically in the disk, or that particular disk we call it as job pool or job queue. Now we already know that these processes or the programs they have to be moved to the main memory for execution, right? Now, who is responsible for this action? Who will select the processes from this job pool or the job queue, and then it will be those selected processes or programs will be loaded into the main memory. Now, this is the work of long-term schedulers or the job schedulers. Okay, as the name suggests, job schedulers, right? So these are the jobs or processes. Okay, so the group of processes or multiple processes they had to be selected and they have to be moved and placed into the main memory. Now this work will be done by your long term schedulers or the job schedulers. Okay, next we have short term schedulers or CPU schedulers. Okay, now say suppose these processes, long term scheduler has placed these processes p1 p2 like up to p10 in the main memory. Okay, now what has to be done for a process or a program to be executed? CPU has to be allocated to it, right? Now that is the work of your short-term scheduler or the CPU scheduler. So what it will do is like, so out of these processes available in the main memory, your short-term scheduler or the CPU scheduler, it will select any one of the, or it would select multiple processes that has to be executed, or they are ready. It selects the processes that are ready to be executed and it will allocate memory to these processors. Okay, now I'll repeat once again. We have two types of schedulers. One is long term, or it is called as job scheduler. Another one is short term, or it is called as CPU schedulers. So concentrate on these terms, job schedulers and CPU schedulers. You'll get to know the difference. Job schedulers or the long term schedulers, its work is to select the processes from the job pool or the job queue and move or load them into the main memory. Now, short-term scheduler or CPU scheduler's job is to select the process that are ready for execution and allocate CPU to them. Okay. Now, the primary difference between these two schedulers it lies in the frequency of execution. Okay. So, how frequently you execute these two particular schedulers? So, the short-term scheduler it must select a new process for the CPU frequently, right? Now a process may execute for only a millisecond, few milliseconds before waiting for an IO request. Now this short-term scheduler or your CPU scheduler it executes at least once every 100 milliseconds. Okay, why? Because You have to select the processes frequently and you have to allocate CPU to them. That's why the short-term schedulers would be executed frequently. Now these long-term schedulers, that is selecting of the multiple process from the job pool and moving them to the main memory. So these long-term schedulers would execute it less frequently. Maybe minutes may separate the creation of one process and the next. The long-term scheduler, it controls the degree of multiprogramming, that is the number of processes in the memory. So if the degree of multiprogramming is stable, that means average rate of the process creation is equal to the average departure rate. The creation means moving the process into the main memory, and termination or departure means the termination of the processes. If it is equal, then the long-term scheduler may be invoked only when the process leaves the system or only when the process terminates the system. So, because of this long interval between the executions, your long-term scheduler, it can afford to take more time to decide which process should be selected for execution. Again, it is important that the long-term scheduler, it has to make a careful decision. Why? Because in most of the processes can be described as IO bound processes or CPU bound processes. That means IO bound process means it is the one that spends most of its time doing IO operation rather than the computation. Then CPU bound processes, what it will do, it spends most of its time in computation rather than your IO. Okay. So it is your long-term scheduler's duty to have a proper or good process mix, like 50% of your CPU bound process and then 50% of your computational or CPU bound process. So your long-term scheduler's duty is to have a proper mix of these processes, select those processes and then move it to the main memory. Say if suppose your long-term scheduler selects all IO bound processes, then what will be happening? So in this case, what will happen is like your ready queue will almost be empty. Why? Because whenever the process execute, it goes for a IO. Next process would be selected, again it goes for IO. Likewise, your ready queue, this ready queue would be empty. In contrast, if say suppose your long-term schedulers it select all the CPU bound processes, then what will happen? Your IO waiting queue would be device queue would be empty. So your devices will be unused and again your system would be unbalanced, right? Now your system with the best performance it should have, whenever you want your system to be the performance should be best, that time you should have a good combination, that is the mix of your CPU bound process as well as the IO bound process, and it is the duty of your long term schedulers. So, in some systems, the long term scheduler may be absent or it would be minimal. So, for example, the time sharing systems such as your Unix and Windows, so often they have no long term scheduler, but they simply put every new process in the memory for the short term scheduler. Now, the stability of these systems it depends on the either on the physical limitation such as the number of available terminals or on the self-adjusting nature of the human users. If the performance declines to unacceptable levels on a multi-user system, then some users will simply quit. Okay. Now, some operating systems such as your time sharing system, it may introduce another type of scheduler called as medium term scheduler. Okay. So, why this medium term scheduler is needed? What is the use of it? Right? Now, the idea behind this medium term scheduler is that sometimes it can be advantageous to remove the processes from the main memory, okay, and then reduce the degree of multiprogramming. So, what can be done is like, so I hope you know this portion of the diagram, right? We had seen this already, the below portion. Now, the medium term scheduler, what it does is like, so whenever you have a process in the ready queue and say, suppose it is executing, okay, and say whenever it is executing, a high priority process comes and the CPU has to be allocated to it. At that time, what can be done is like the process which is already executing, that is your low priority process, can be swapped out of your main memory Swapped out means it can be moved out of your main memory. This one, okay. Whenever it is executing, it can be moved out. That is swapped out from the main memory. It can be put in a partially executed swapped out process queue. Then once the high priority process, it leaves the system, these partially executed processes can be again swapped into the ready queue, or it can be moved in back to the ready queue and its execution can be carried out. Okay. Now this we call it as swapping. Okay, this process we call it as swapping. The process whatever is executing or it is in the ready queue, it will be swapped out or moved out of the main memory, and later it would be again swapped in or moved in into the ready queue. Now this would be done by a scheduler called as your medium term scheduler. So the swapping may be necessary to improve the process mix, or because a change in the memory requirements have overcommitted your available memory, requiring memory to be freed up. So at that time this medium term scheduler will come into picture. So swapping we will again discuss in the further chapters. Okay. Next we will move on to the context switch. So So let's study about this context switch. So context switch, it means switching of your CPU to any other process that requires performing a state save of the current process and a state restore of a different process. Now this process we call it as a context switch. So if you could remember the diagram which we had seen while discussing the PCB. Okay, let me just show you that diagram. So yeah, this is the diagram. So what will happen is, say suppose process P0 it is executing, and say if some interrupt occurs or system call, it calls for a system call. That at that particular time what has to be done is the state of this particular process P0 which was running, it has to be saved onto its PCB. Then say suppose in the meantime your CPU cannot be idle, right? It has to do some work. So what can be done is like the another process which was idle, it can be brought to the, or it can be given to the CPU for executing. At that time what have to be done is the process P1's state has to be restored from its PCB. Then it can start executing. So this we call it as a context switch. Okay, the switching of the CPU from one process to another process, whenever this happens, it requires the state save of one process and state reload of another process. Now this we call it as a context switch. So whenever this context switch occurs, the kernel, it saves the context of the old process in its PCB, and it loads the saved content or context of the new process that is scheduled to be run. Okay, now context switch is that context switch time is pure overhead, because the system does not do any useful work while switching from one process to another process. Its speed varies from machine to machine depending on the your memory speed, number of registers that must be copied, and the existence of some special instructions such as your single instructions to be load or store all registers. Basically, the speeds would be like few milliseconds. That's it for today. We'll conclude our session. Thank you.